set of talks plus common panel discussion at the end format. So remember your questions for our speaker and address them during the common panel discussion at the end of the session. So the first talk here is Kristinn Thórisson from the beautiful nation of Iceland, presenting some work from himself and his colleagues on flexible task environments for comprehensive evaluations of AI systems, automatic learners, and so on. Take it away.
Can you hear me on this mic? Is this okay? Okay, good. All right. Thanks, Ben and Jordi, and hello, everyone. Very good to see you all. So I'm not quite sure how much time I have, so let me move along briskly if I am able to. 15 minutes. That's okay. So, without further ado, here's the outline. No, just kidding. So, I wanted to spend some time on motivation because, frankly, the main contribution here is a set of requirements. And unless there are engineers in this crowd, engineers used to working with starting from requirements when they do their work? Okay, good. Then, and I'm not wasting your time here by emphasizing that part. And a draft of a solution to these requirements, which you may or may not agree with, which would be absolutely perfectly fine with me. And then some conclusions to be drawn. So the backstory is this. We had a reinforcement learner that we had some data for, and we wanted to enhance it with continuous input and output features. And we asked the question, so we have a reinforcement learner X and X prime, and we asked the questions, which is better, this particular implementation, the new one, the old one, or the modified version? Can X prime even replicate what X did? And we already have data to prove that X can do certain things. Now, what we had is basically old performance data for X on a task, no verification of X prime, because that was the new thing, no current setup to run the old task, and scarce documentation at best. So, the old test was a major hassle to set up, but the data it provided gave us a lot of good information about X. And X prime had features that were not tested or included in test one. So, so here are the possibilities. It's a short list. Basically, we could reconstruct test one and rerun it for both X and X prime. That would be a lot of work. We could construct a new test, T2, and run it for X prime, and then compare it to the old data, but it wouldn't be quite comparable, probably, because X prime has new features. And so we would have to know how to compare this data. Or we could construct a new task, T2, that subsumed task 1, and run it on both. But then we'd have to have some information about the relationship still between T1 and T2. So what did we do? Well, we did none of the above, actually. We did something else. We started asking questions. As we asked these questions and we dug more and more in, we realized, there's a lot of performance data available on various learners. And by the way, these learners, you can't really prove them mathematically, typically, because, you need to run them in a simulation to really know how they perform on various parameters. Now, the problem is that all of this performance data out there, it varies widely. So how do you compare a performance of algorithm X on task A and the performance of algorithm Y on task B if you can't compare tasks A and B in any way, shape, or form? So just a very short glimpse of what this problem is. It's, for instance, here we have 4 very popular tasks for simplistic learners. I know this is an AGI crowd, and we'll get to the AGI stuff, but I truly think that this is completely relevant and can be extrapolated. So the pole balancing task, the mountain car task, and diving for gold task, these are very popular tasks in machine learning. Now, if algorithm A performs well on pole balancing, can you say anything about how it will perform on the diving for gold task? Not really, because these tasks, and if these are these very simple tasks, how are we ever going to hope for doing this for complex tasks like the tasks we really need for AGIs? So there's already a lot of tasks proposed, but typically the tasks are targeted to a small set of learners. So for instance, those tasks that I showed you are very popular for reinforcement learners, but throwing an AGI at these tasks, pole balancing, it seems like using a sledgehammer to drive in or to plant a flower. And even starting with those simple tasks, is there a way to grow them so that they become complex more complex as your algorithms become more capable? Well, that's a problem. And lastly, typically, because these tasks are kind of targeted to answer specific questions about specific learners, they're not very applicable to AGI systems, so it's very hard to compare. So that's a special thing we have in AGI, in the AGI community, is all of the tests that the rest of the machine learning, this is changing now, as the gap is slightly closing with inroads from deep learning and other techniques, but it's still, by and large, a problem. And here's the gap. This is a really wide gap from the Turing test to Pacman, and people throw these things in there, and they just think somehow these can be compared. Even more recent ones, which I'm a big fan of, creativity tests. The problem isn't only sort of comparing these between AGI and simplistic learners. It's really also, it's an all-way problem. You can't really compare these, even at the low end, you can't compare Pong to Pac-Man. So, so we know comparison is difficult. But even a bigger problem is that most AGI-centered evaluation proposals that are out there are limited to assessing the system at a single point in time, i.e., you've got a system, now it has learned some stuff, now let's evaluate it. Well, this is a problem because for general learners, you should also assess other things like learning capacity, lifelong learning and forgetting, transfer learning, cognitive development, These are all somehow left out of pretty much every single proposal as far as I've seen. So, with the backstory now in hand, what we came to the conclusion of is that we need a framework that allows us to construct tasks in a transparent way so that they can be grown in predictable ways, so that they are transparent enough that they can be compared, even a complex version of the same task, all the way up to very highly complex tasks and very simple tasks. That would be really nice to have. Just to reiterate, and I haven't actually touched on this point, just so we're on the same page, why do we want to evaluate AI systems? Well, I think it should be pretty clear to everyone here, but just to go through it quickly, we want to assess our research progress. So that was the example here in the reinforcement learning scenario that we had, reinforcement learner X and X prime. We want to evaluate strengths and weaknesses. So that's that was also the case in this reinforcement learning scenario. And we want to compare not just systems and assess progress, but we also want to compare approaches and so on. So comparing sets of learners sprouting from the same methodology, say. Right. So what is the goal that we set ourselves? We want to develop a framework for constructing transparent task environments with some properties, and I'll get into more detail in a second. we want to be able to easily construct, or relatively easily, abstract task environments and variants thereof that are amenable to automatic generation so that we can give the system a relatively high-level spec. We want a task centered on these features, but we also want you to generate random, possibly, variations on it that still are comparable to the original task. So that even though it's random, it's randomly sampled from a variety of diversions and variations, you still have the possibility to say, well, this is random, yes, but it's comparable to that one except for XYZ. And XYZ have certain properties, and therefore we can predict that certain things will happen, or that the task has certain properties. And so that's the third thing. We want to be able to easily analyze everything that really matters for each scenario. So what features should these, what should this framework give us? The framework will give us some ways of constructing environments that adhere to certain requirements. And so this is a set, I think, of 8 or 9 points. So after much thinking about this, we classified it according to the following list. Determinism. You want to be able to have a slider or a reasonably high-resolution variable that you can set from complete determinism of a task to partial, or even down to 0, but that's noise, so I don't think that's really sensible. However, you might want to see if some learner, how some learner breaks down as you slide this slider down to from 100% down to 0. That would be a nice thing to automatically set up. Learner X, test it on how it responds to the non-deterministic environment. Periodicity, it should support temporal patterns, which means it should have ability to handle time. And controllable continuity, so the resolution of variables is another way of thinking about that. You shouldn't have to be given or have predefined resolution of the space in which the variables live. Asynchronicity. Events should be possible to happen at arbitrary time scales. This is, of course, important for systems that can shift their attention from the minute to the gross features of a task environment. Dynamism, things need to be able to move, but you may not want that feature. All of these things should be able to turn down in any way you see fit. Observability, you should be able to control how much is observable to the system. Controllability, how much the system can, how the system actually controls the environment. This should be tunable so that, for instance, to make a variable harder or easier to control using latencies in response, etc. Multiple parallel causal chains, this would, of course, be necessary to represent anything remotely resembling the real world. And although if there are any philosophers here, let's say the physical world. Number of agents, yes, you should have to be able to put in a bunch of agents in there. So here is what we came up with. Now, so that's the set of requirements. This is really, I think, a complete list. If we had a perfect system, this would be the system. It would allow us to, it would give us these, it would meet these requirements. It would give us these features. So I wanted to show you an early draft that of a proposal that we have, just to put some flesh on this so that you start to get a better idea of, and I think I have probably just 1 minute left now, since you were so hungry for coffee upstairs that, anyway. So we propose to build a task environment through a set of time-dependent variables with relationships. Now, there's nothing really earth-shattering here. This is not rocket science, really, but it kind of shows the level of resolution that we think may be needed. So here's a graphical representation of a task. This is like a navigation task of a robot in a 3D environment, 2D environment. And so you list the rewards, the sensations, the control that the robot has at the bottom, the red circles, some hidden variables, in fact, and data flow, and maybe some delayed flows as well. Here's a program form of this spec for an environment. And this example of a task produced by these Lego bricks is discrete, fully observable, and static. Now, if we wanted to change this, we could make it continuous by adding, for instance, an angle at, represented by a float, say, that was thrown in there and was yet another variable that the robot could control. Yeah. Okay. So I should be done now. Some other ideas to throw in here is decrease observability. You get a typically harder to do task and so on. And so half a minute and then I'm done. Framework allows addition of time pressure, deadlines. I'm not going to show that now, but some of those ideas are outlined in the paper. Complex preconditions and complex interactions and modulating dependencies, which is nice. So does it scale? We think so. First of all, it's really nicely amenable to automatic construction, piecewise or fully. And in the worst case scenario, if you were to give a system the high-level spec, it could search brute force for a solution that would meet those high-level requirements for a task. Now, there's some work remaining. Obviously, this is just an outline, a sketched outline, but we may not be able to fully address all of the requirements listed. Nevertheless, I think it's important to have them there. We need to create a more fully fledged formalism so that we can see sort of how far we can push this. One way to do that would be to transcribe well-known popular tasks. And then, of course, beyond that, we need, of course, good measures for describing task environment complexity, for describing cognitive energy expenditure, and then we can develop a proper measure for the difficulty of a task, given a measurement for environment complexity and cognitive load, if you can call it that. And yeah, and that's it for now. Thank you.
Thank you, Dr. Thórisson. The next speaker, yes, Dr. José Hernández Ohaya.